Okay, so here we're starting next section, use geometry probability. I'm going to focus this, at least try to. Okay, so it says the probability of an event is a measure of the likelihood that the event will occur. It is a number between 0 and 1 inclusive and can be expressed as a fraction, decimal, or percent. The probability of an event A is written as P of A, where, let's see, God, my eyes that bad? Well, if it's 0, it's impossible that it's going to happen. If you have 0.25, you have a small possibility. 0.5, so it's equally likely to occur or not occur. That's 50%. 75 or 0.75 means it's likely, so you have a good chance of it happening. And 1 is certain. That means it's always going to happen. So a geometric probability is a ratio that involves a geometric measure such as length or area. So here we have our first key concept, and it says probability and length. Let AB, which is the whole thing, be a segment that contains the segment CD. If a point K on AB is chosen at random, then the probability that it is on CD is the ratio of the length of CD to the length of AB. So what that says is, so the chance of a point landing inside here is that length, the smaller one, over the entire length itself. So for example 1, which I have over here. So it says find the probability, oh my goodness, find the probability that a point chosen at random on PQ, so from here to here, is on RS, from here to here. So according to our probability, the probability of a point is on RS is equal to, well, that length over PQ. So we have to figure out what those distances are. So RS, well, this is 4, 6, but you would do 4 minus, because you go in that direction, to -2, which is a negative, and a negative is a positive, so that ends up being 4 plus 2, which is 6. I looked at it at the number line itself. From 4 to 0, that's 4. To -2, it's 6. So it's 6. Then PQ, which is from -5 to 5, so you automatically know that's 10. But again, 5 minus, going in that direction, a -5, a negative and a negative is a positive. So that length is 10. Then you would divide, because you want it as either a decimal or a percent. So 6, put your decimal in your answer. Can't go into 6, but it can go into 60. 6 times, it terminates. So 0.6 or 60%, either one. 0.6, it's a good chance that this is going to happen. So that's example 1. Example 2, I'm going to do it right from the book itself. It's way too much to copy. Okay, I don't even know if that's clear enough because for my eyes it's not. Excuse me. Oh my God, I choked on my own saliva. So it says a monorail runs every 12 minutes. The ride from the station near your home to the station near your work takes 9 minutes. One morning, you arrive at the station near your home at 8:46. You want to get to the station near your work by 8:58. What is the probability you will get there by 8:58? So I'm just going to read through the solution and make it easy. So step 1, find the longest you can wait for the monorail and still get to the station near your work by 8:58. The ride takes 9 minutes. So you need to catch the monorail no later than 9 minutes before 8:58 or 8:49. The longest you can wait is 3 minutes. So 8:49, 8:40, and the difference of 8:46 is 3 minutes. So they did a model of the time, 8:46 to 8:58. Get a little closer. There we go. So the monorail runs every 12 minutes. So it will arrive in 12 minutes or less. You need it to arrive within 3 minutes. So here we have from 8:46 to 8:58, which represents the 12 minutes. So this is your 3 minutes right here. So you want to find that probability that you get to the station by 8:58. So the favorable time is 3 minutes over the entire time, which is 12 minutes. So 1/4. So you have a 25% chance to getting to the station within those 12 minutes. Make it. So that's example 2. Now we're on to our next key concept, which is when you deal with area. There we go. So make sure you copy the key concept. It says, my goodness gracious. Let J be a region that contains region M. If a point K in J is chosen at random, then the probability that it is in the region M is the ratio of the area of M to the area of J. So the probability of landing in M is the area of M itself, the smaller one on the inside, over the entire area. Now we're going to look at example 3. I did draw a picture for this one. So it says the diameter of the target shown at the right is 80 centimeters. The diameter of the red circle on the target is 16 centimeters. An arrow is shot and hits the target. If the arrow is equally likely to land on any point on the target, what is the probability it lands in the red circle? So here we have our target. It's not a pretty target, but so we want the probability that we hit that red target. What is the chance that we can actually hit that target? So the probability arrow lands in red region. So that is the area of the red circle over the area of the target itself. Well, you have to know that area of a circle. So the area of a circle is equal to pi r squared. So that we need that piece of information as well to help us. So now You need the radius. They have given us the diameters. So the relationship between the diameter and radius is you divide by 2. So the radius of the target is going to be half that, which is 40. And then the radius of our red circle is going to be half the 16, which is 8. So now we can plug it in. So the area of the red circle, which is this one, so pi r squared over the area of the target, which is pi r squared. Well, the pi's cancel, and we're left with that. And now we're going to divide. So 8 squared is 64 over 40 squared, which is 1600. And then we divide. So 64 divided by 1600. And we get 0.04. So we have a 4% chance of hitting that target. Example 5 is kind of complicated. I recommend that you go back to the textbook and look at it and figure it out. And that's the end of 11.4. Make sure that you took notes. Go back to the textbook and look at example 4. Okay, guys, bye.